The process of finding the shortest distance between two lines that never meet and are not parallel begins with a transition from abstract calculation to visual proof, as detailed in the derivation sheet. This journey is structured around two distinct perspectives: the step-by-step logic of the system's actions and the shifting states of the visual models. The systematic workflow. The progression starts by identifying the specific locations on each line that are nearest to one another. Once these locations are identified, the system performs an analytical check to confirm that a bridge connecting these 2 points is perfectly perpendicular to the direction of both lines. With the groundwork laid, the system moves into a visual verification phase. A static three-dimensional model is generated to provide a clear, fixed view of the lines and the shortest path between them. This allows for a definitive visual confirmation that the connection is indeed perpendicular to the tangent directions of the lines at their points of closest approach. The dynamic exploration. After establishing this static truth, the narrative shifts into an active exploration. Rather than looking at a frozen moment in time, the system introduces motion to investigate how the distance changes as the connection points move away from their optimal positions. A synchronized probe is initiated, causing the points to slide back and forth along their respective lines in a balanced, rhythmic cycle. During most of this movement, the points are not at their closest possible proximity. Consequently, the bridge between them is not perpendicular to the lines, and the system displays it in a neutral gray. The causal discovery. The climax of the exploration occurs at a single, recurring instant during the oscillation. When the movement reaches the exact coordinates identified in the initial analysis, the system identifies a direct causal link between distance and geometry. At this precise moment, 3 events coincide. The distance between the points reaches its absolute minimum. The connection vector becomes perfectly perpendicular to both lines simultaneously. A visual signal, a bright green highlight, triggers to confirm that the optimal state has been reached. This dynamic transition proves that the shortest path is not just a random occurrence, but is fundamentally necessitated by the perpendicular alignment of the bridge connecting the two lines.